Good morning and welcome to Indices 1. This will be a two-part lesson series and today we'll be looking at the basics of indices. Hopefully you managed to download the worksheets and have a go at these questions to start. We will look at the solutions to these now. Focusing on the top left question, a simple divide fractions question. If you ever divide fractions, you should be remembering KCF. This stands for keep, change, and flip. Okay, and you do it in that order. You keep the first fraction, you change this divide to a times, and you flip the last fraction. Hopefully you managed to look at the fraction questions if you're unsure on this, and the lessons that we've done previously. But what would we get? This would keep, and we would leave it as 3/4. We would change this to a times, and we would flip or do the reciprocal of the last fraction, which would be 8/5. Timesing across, very simple, no need for anything other than timesing straight across. 3 times 8 would be 24, and 4 times 5 would be 20. Now, two things can be done with this fraction. One, it is improper, it is top heavy, and two, it can be simplified. So if we simplify first, you would get 12/10, which is 6/5. Still, this is improper, so we could change this to 1/1 and 1/5 left over. If you're unsure on any of that, go back and look at my fractions 2 lesson where we looked at dividing fractions. Moving over to this quite simple looking question. It's in here for a reason, because the indice questions require you to be able to add and subtract negative numbers. Here we've got 5 plus minus 2. Well, a plus minus 2, if you add on a negative, it just means a minus. So we've got 5 minus 2, which is 3. Probably very straightforward for most of you, but something that we need to be clear on. To the bottom left, if D is equal to 6, work out 8D plus 3. Well, remember, 8D means 8 times D. So if we know D is 6, 8 times 6 is 48. So 8 times 6 is what this is saying, plus 3. So that equals to 48 plus 3, which is 51. Substitution is this topic, something that will be coming up in the lesson series. Okay, we have to substitute in. And finally, a solve question. When you're solving an equation, we're looking to get, in this case, Q, the unknown, on its own. Right now, you should be thinking that it is trapped inside this bracket. To untrap it, or to expand this bracket, is the technical term. We often draw lines to help us, and remember, you do this times this, and this one times this one. So 2 times 7Q would be 14Q. 2 times minus 7. Now, we've discussed this in a few lessons that I've done so far. This minus is not floating, it is attached to this 7, so it is minus 7. 2 times minus 7, a mixture makes a minus, is minus 14. And that is going to be equal to 56. Okay, so now we need to solve. So we've expanded. To solve this, we need to, first of all, get rid of this minus 14s by doing the opposite. Plus 14 to both sides. If we've just removed this from this side, we're left with 14Q. And don't forget, you need to do 56 plus 14, which is 70. This, remember, means 14 times Q, the opposite of times by Q. And times by 14 is to divide by 14. So we'd end up with Q is how many 14s go into 70. If you're unsure, do a bus stop or write a fraction and simplify, but it would be 5. Okay, so hopefully you managed to get all, if not most of those answers correct. And we will move on to laws of indices. Now, if you're in year 8, 9, 10, these are really important. Laws of indices come up in both the foundation and the higher exam, and it is something that is easy marks if you can remember the laws and you know how to use them. Loads of students forget the laws and they forget how to use them and they get them mixed up in their head. So today we're going to take an in-depth look at each law for the basics and how they progress into difficult looking questions, but how do we use those basic laws to help answer the difficult questions. So just to be clear, an indice is a word for power, and we know a power looks like this to here. So what we refer to this as, this 4 is the base. So the technical mathematical language for this here is the base, and this is the indice, or often referred to as the power. So 4 squared. 4 is an integer, so we could actually work out 4 squared. We know it is 16. But just to be clear, that is your indice and that is your base. It can be done with a base that is algebra, an unknown, so you could have x to the power 4. And just remember, what does that mean? And this is not a basic indice lesson, but this is a laws lesson, but x times x times x times x is what x to the power 4 actually means. And this is a really, really, really important fact that often gets overlooked. If there is no power, so if you just have p, then technically the power is 1. So it's 1. And that is going to be such a useful piece of understanding to help us answer and not make mistakes on the difficult indice questions. This is a really, really, really useful piece of information. If there is no power, so if you've just got a, it technically means a to the power 1. If you've just got 3, the number 3, technically there's a power 1, we just don't write it. Very similar to if we say x, that technically means 1x. We're just lazy, mathematicians are lazy, and it just doesn't look right. 1x, it's easier just to write x. So we don't write 1x usually, we just write x. We wouldn't write 1a, we would just write a. So knowing that if there is no power, the power is technically 1. It is not 0, that is a very common misconception. If there is no power, it is 1. And that's going to be useful, and you'll see why later. So, the first and most basic law there is, and law is just a word for rules, is a to the power 0. And these laws that I'm going to give you will be written with a's. And that is just a way to say we could replace this a with any number. So it's a generic way to write it so you can apply it to anything. But what this says here, and you might want to add this note, anything to the power 0 will always equal 1. So this law here tells us that if you have anything here, so it could be a, it could be a number 10, anything to the power 0, it will always equal 1. And if you don't believe me, you can get your calculator and you can put in loads of numbers and you can make it to the power 0. So for example, if I clear my calculator, if I put in 200, raise it to the power 0 and press equals, I get 1. Okay, so anything to the power 0 is always 1. And I believe you did not see that, so I'll just get that up properly. So hopefully you can see that now. So 200 to the power 0 equals 1. If you did 1,000,000 to the power 0, it gives you 1. So really, really basic rule, but one that most GCSE students get wrong. They get it confused. So let's have a look how we can use this. So I've got 3 examples here. Example 1, x to the power 0. Well, these are very straightforward. Anything to the power 0 is 1. So I'm sure you're thinking, well, x to the power 0 must be 1. So the answer to that first one is 1. Example 2, 50,002 to the power 0. Again, just 1. Very simply, 1. Example 3, 8x to the power 0. Now this is where we just have to be a little bit careful. What do we know? We know that x to the power 0 is 1. And what does 8x technically mean? It means 8 times x. So if we've got 8 times x to the 0, that is saying 8 times effectively 1. So the answer to this is 8 times 1, because remember, x to the 0 goes to 1, and 8 times 1 is 8. So there's an example where the answer is not just simply 1, but knowing that x to 0 is 1 helps us get to the complete answer of 8 in this case. Okay? So that is the most basic indice law that you can remember. If it comes up in a GCSE paper, it's an easy mark. You get a mark for writing 1 most of the time. Law number 2. So you may have seen this before, and it may be ringing some bells. And if you're in year 8, you might not have seen it yet. And again, I've written it generically here, using A, N, and M. And I'll explain what that means. So what we have, this says any base of A to the power of a number or anything with a same base of A to another power, there's a law. So the first thing we should just say here is this law only works if you have the same base. So this only works if you have the same base. And this may seem a little bit confusing for a second, but as soon as you start seeing it with examples, it will make perfect sense. So if you have the same base raised to a power and you are timesing it, so this is all about timesing the same base with different powers, there is a rule that says this: we can keep the base the same and you simply add the powers. So you keep the base the same and you add the powers, okay? And again, it always looks a little bit confusing and a little bit scary if you haven't seen it before and you are looking at those letters thinking, what is going on? But simply, if you have the same base and you are timesing them together, you add the powers. Okay. So what does that look like? Example 1. Let's see it in action. We have 3 squared times by 3 to the power 5. Well, the first thing we should check, do we have the same base? Yes, we do. We have the same base. Are we timesing them? Yes, we are. Well, the rule says if you have the same base and you're timesing them, you keep the base the same and you add the powers. So what we're going to do here, and I'll explain why this is, we're going to keep the base as 3 and we're going to add the powers. So we're going to do 2 plus 5 is 7. So the answer to this is 3 to the power 7. Sometimes I'll ask you to write that out as a whole number because 3 to the power 7, remember, means 3 times 3 times 3, 7 times. But they wouldn't expect you to do that without a calculator. So why is it 3 to the power 7? Why does this rule work? Why, when we times, do we add? Why is that? Well, it's for this reason. Let's break down what 3 squared means. 3 squared, remember, means 3 times 3. Then we've got a times in the middle. Then we've got 3 to the power 5. What does 3 to the power 5 mean? 3 times 3 times 3, 5 times times 3 times 3. So that is what this question's saying. And if you count how many 3's I've got there, I've got 1, 2, 3, 4, 5, 6, 7. I've got 7. I've got 3 to the power 7. And we know 3 to the power 7 means 3 times itself 7 times. So that is why you can add the powers. It is not magic. It is based on logic. But all you need to know is if you've got the same base, and again, it only works if you've got the same base, and you times in, you add the powers. Okay. Example 2. And this is where they start to sort of throw extra things at you. I've got x to the power 6 times by x to the minus 3. Okay. First question, do they share the same base? Yes, they do. Remember, if they share the same base, you can use this law. It is times, so the rule when we times, remember, is you add the powers. But they've put a minus in here, so you have to be a little bit careful. So remember, the base will stay the same. It will stay as x, and we have to add the power. And this is why the starter question had a minus and a plus question in it. We've got 6, add minus 3. Well, if you add on a minus, it means take away, so that just becomes 6, take away 3, which is 3. So the answer to this question is x to the power 3, because 6 minus 3 is 3. Okay. The next two examples are where we keep that logic of understanding the law 1, or law 2, sorry, what we've just learned, and we combine it with some whole numbers as well. So we've got 2y squared times 3y to the power 5. Now, if those whole numbers, the 2 and the 3, were not there, it's quite a straightforward question. You've got the same base, there's a times, so you add the power. However, with the introduction of the 2 and the 3 here, students get a little bit confused. But you have to remember that multiplication is commutative, which means you can do it in any order. So remember, 2 times 3 is 6, and 3 times 2 is 6. So even though they are the wrong way around, the opposite way around I should say, you get the same answer. So here, what we're going to do is we're going to treat our whole numbers together, because we could write this as 2 times 3 times y squared times y5. That would be the same thing, just written in a different order. And it becomes a lot clearer when you think of it like that. Because you just do 2 times 3, and then you add these powers together, given the rule. But what we're going to do is we're going to take the whole numbers, the 2 and the 3, we're going to times those together. Because remember, it says times. 2 times 3 is 6. Now we're going to look at our y squared and our y to the power 5, and we're going to say, oh, I'm timesing. Do I have the same base? Yes. What do I do when I times? I add the powers. So I'm going to keep the base the same as y, and I'm going to add 5 and 2, which is 7. So the final answer is 6y to the power 7. Because I am allowed to take the whole number separately. So 2 times the 3 is 6. And then remember, y squared times y5 lets me add the powers because the base is the same. So I get the same base y plus the 2 powers gives me 7. Okay, and then example 4 is an extension of this. And this is going to recall back to something I said right near the beginning. Very similar example to this, there's just more going on. We've got 5a b cubed times 2a to the minus 4 b cubed. So we're going to use the same method we just did in example 3, where we can take each thing individually, and I'll highlight to show how I'm doing this. So I'm going to take my whole numbers. So I've got a 5 times a 2. So I'm going to do the 5 times the 2 first, which is simply 10. Now I'm going to look at my a's. Now this is going to refer back to something that we spoke about a second ago. Got a and a to the minus 4. If we think a, there is no power. So what's my rule? I'm timesing, so I need to add the powers, but there is no power. However, right at the beginning I discussed here, if there is no power or no indice, it is 1. So a really good exam skill that you can do right now, whenever you see a unknown like this A with no power and you're doing indices, you can just put a 1 in. It's going to make things much easier. Just slip a little 1 in there because that's what it technically means. So we're going to do a to the power 1 times by a to the minus 4. They share the same base, so I can use the law where I can add the powers. So we're going to do 1 add minus 4 and 1 add minus 4. Hopefully you're thinking that is minus 3. So you keep the base the same as a, and it becomes minus 3 the power. Okay. So I'll just colour coordinate this for you. That's where that came from, and the 10 has come from there. Then finally we need to just do the b's. So it's the same thing as the last question, there's just more unknowns, there's more indices to deal with. We've got b cubed times by b cubed. Well, bases are the same, so I can highlight these in the same colour. And we're going to do the rule on this, we're going to do the law on this. B cubed times b cubed, I add the powers, so I get b to the power 6. So we end up with my final answer. It looks very colourful, but my final answer, if I write it with no colour underneath, is 10a to the minus 3, b to the 6. So all you do, they look very, very intimidating, but all you do is break it down into each base and each whole number, if there is one, and you just use this law up here. Okay, so as you can see, each example used the same law, but just progressed in difficulty as we got down to the final one. And you'll have an opportunity to practice these on some questions I've got near the end. But that is law 2. So we've looked at now 2 laws. Very basic, but as you can see, they do build where you have to be careful. So moving on to law 3. Well, naturally, we've just looked at how to multiply 2 bases with powers the same, or the same base with different powers. Now we're going to look at how to divide. Now, just to be clear, there's 2 ways we can write divide. We can put the actual divide sign in, or we can write it as a fraction. They both mean divide, and hopefully you're clear on that. So again, looks quite confusing, there's loads of letters, but this basically says if you have the same base, same as last one, if you have the same base, in this case a, with a power and you are dividing, the indice law is this. You keep the base the same, so in this case a for the generic example, and you take away the powers. So you do, and that, you know, that makes sense. If you, when you times, you add the powers, surely when you divide, you take away the powers. So generally, if you can remember one of the rules, logic will tell you the other rule. So we're going to do n, and again, it's the first one minus the second one. So it's this one, take away this one. So that's going to be n minus m. So you keep the base the same, and then you simply subtract the powers. Okay, and that would be the same if it looks like this, with a divide written as a fraction. So again, we're going to practice these, and hopefully they'll become clearer when we look at examples, but we'll practice these on some examples here. Remember, when you divide, you have the same base and you take the powers away. So example 1, 6 cubed divided by 6 squared. Well, do they share the same base? Yes, they do. They both have 6 as the base. So when you have the same base and you're dividing, you simply subtract the powers. So we just get 6, the base stays the same, and then 3 minus 2 is 1. And remember, another way to write 6 to the power 1 is simply 6 without a power. So very basic example there. Similar to the last question, or the last law, we're going to build on difficulty. Example 2, set of numbers, we've got algebra, we've got letters. And it's written in a different format. We've got x to the power 5 divided by x to the minus 2. Now this is where they start to try and trip you up with negatives, because remember, if you have the same base, that's the first thing you need to check. Is the base the same? You can't do these laws if there's a different base. Yes, the base is the same, they're both x. We're dividing, so you should be thinking, I take away the powers, and this is where we have to be really careful. We need to do 5 minus 2. So we're going to keep the base the same, and our power is going to become whatever 5 minus 2 is. So this is where they try to trip you up by putting a double negative in over here, look. Because the rule says we need to minus the powers, and the second power is negative, so you end up with a double negative, which you should know becomes a plus. So the power for this one, a lot of students will write 3, but it's not 3. The power for this one is 5 minus 2, and 5 minus 2 means plus 2. So 5 plus 2 is 7. Okay, and I've just put that little diagram there, so when you look back at your notes in the future, if you've forgotten them, you can see clearly how we got this 7. Because we minus the powers and there was a double negative. Okay, so we've got a double negative there, x to the 7. And again, the next two are just going to be all based upon the same law, but just have extra stuff thrown in at you. So, example 3. We've got 45 a cubed divided by 9 a to the power 6. Well, we're dividing, we've got some spaces that are the same, so we could use the law there, but we've also got some whole numbers now. Very, very similar to the multiplying, we can break these down into different aspects. So we've got a 45 divided by a 9. So we work that bit out first. What is 45 divided by 9? Well, hopefully you're thinking, that's 5. 45 divided by 9 is 5. And then you're going to focus on the indices. First thing you should check, do they have the same base? Yes, they do. So the same base would be a in this case. So we're doing a cubed divided by a6. Well, what is the rule when we divide? You minus. So we're doing 3 minus 6. Well, 3 minus 6, we keep the base the same as a. 3 minus 6 would be minus 3. So again, I'll just put a little arrow to that to explain where it's come from. It's come from 3 minus 6. Because the law says you do the first power minus the second power. And 3 minus 6 takes you down to negative 3. Okay, so you treat the whole numbers, do them separately. You treat the indices separately, and you do those. And then that takes us on to the final example, which, as you can see, a lot more involved, looks a lot harder. But if you stick to those principles of example 3, you should end up with the right answer. And you just have to be careful with the negatives, the double negatives, the powers not being there, you put your own power in. So let's have a look at this. We've got 60, a, b10, c to the power 5, divided by 10, a to the minus 3, b to the 4, and c to the power 5. Well, as you can see, there's a lot of things here, but we can break it down logically into each whole number and each base that is the same. So if we focus on the whole numbers first, we've got 60 divided by 10. Well, hopefully you can answer that in your own head. 60 divided by 10 is 6. So the first part of my answer is 6. A divided by a to the minus 3. Now again, we've discussed if there is no power, the power is simply 1. So the power is 1. They have got the same base, so we can use this law on them. So we've got a to the 1 divided by a to the minus 3. When you divide, you take away the powers. So you have to be a little bit careful here. We've got 1 minus minus 3. Well, 1 minus minus 3. Well, a minus and a minus makes a plus. So that is basically 1 plus 3, which is 4. So the base again stays the same. The power would be 4. So it'd be a to the 4. Moving on to the b's, we've got b to the power 10 divided by b to the power 4, which would be simply b, the base stays the same, minus the powers, 10 minus 4 is 6. And then finally, we have a c, so we can focus on the c. What does the c say? Well, the c says c to the 5 divided by c to the 5. You have to be a little bit careful here. C to the 5 minus c to the 5. Well, you minus the powers, that would give you 0. So this c would be c to the 0. And we know c to the 0 is 1. So we technically need to times this by 1. But timesing by 1 would just give me that anyway. So the c's just cancel essentially in this case. Okay, there's no point timesing this by 1 because you just end up with the same thing that we've got there already. And that will conclude law 3. Again, very simple law. As you can see, it can progress quite quickly into not necessarily difficult questions, just you have to be really careful. I would say they're not difficult. If you're not thinking clearly, you can make obvious mistakes. So breaking it down like I have with the colours there, knowing the laws, knowing the little tricks like a to the nothing is technically a to the 1, and being careful with double negatives is going to make sure you stay on the right path to get the correct answer. So finally, I believe this is the final law before you get to have an opportunity to practice them, will be what we call raising a power to another power. And this is the one that most students make mistakes on. Raising a power to another power. Okay? So what this says, it says we have got some number or some letter with a power and we're going to raise it to another power. So let's have a look what that means. The law states that if you raise a power to a power, you simply keep the base the same and you multiply the two powers together. So this a stays as the base, and you should see a common theme. The base generally stays the same. If you have the same base, that's sort of the green light to use the law. And what generally happens 9 times out of 10, the base stays the same and something happens to the powers. So in this case, we're going to multiply the powers together. And again, can always look a little bit confusing when you are looking at this generic law that I've written for you here. But when you start to put it in context with questions and examples and numbers, it becomes quite straightforward. So if we look at example 1. Example 1 states that we have got x squared and we're going to raise it to the power 3. Well, if you raise a power to a power, you simply multiply. So this is very, very easy. All you do is keep the base as x, and we're going to do 3 times 2. And 3 times 2, remember, is 6. So the answer to that question is simply 6. Example 2 and example 3 is where students go wrong. And I can see why they go wrong, but I'm going to explain now, using things you've seen already, why they get it wrong. So I'm going to show you what the students generally do, and it might be something that you were thinking, and then I'll explain what they've done wrong and what they've missed. So don't copy this down, but this is what students do. They say, right, we've got 2a squared and we're raising it to the power 2. And they know the law, they actually remember the law, I need to multiply these powers together. So they end up with this answer. They say, right, I've got 2a to the power 4, because 2 times 2 is 4, and that's what they write. This is only half correct. What they have failed to do is also raise this 2 to the power 2. So this is what they should have done, so you can copy this down now. First of all, a squared, that has a power, we're going to times those together, that's all good. 2, and we've discussed this, 2 doesn't have a power, but we know the technical power to 2 is 1. Technically, there's a little 1 there, we just don't write it. So what you have to do is the same law, but you have to do it to both terms. Everything that you're raising to the power, because it's in a bracket, needs to be multiplied. So what does that mean? Well, it means that you need to distribute this 2 across both terms. So what do we get? Well, we've got 2 to the power 1 raised to the power 2. Well, the law says you times the powers. So what is 2 times 1? Well, it's just 2. So you end up with 2 to the power 2, because I've multiplied the powers together. Now for the bit that students get right, we've got a squared raised to the power 2 times the powers together would, hopefully you can see, would be a to the power 4. Okay, so our final answer, well, we're not quite done yet, because in these types of questions, they generally keep this bit a low power. We can tidy this up, we can simplify this. What is 2 squared? We know 2 squared is 4. So the answer to this is 2 squared is 4, and then we've got the a to the power 4. So the answer to this question is 4a4. And as you can see, where I wrote the wrong answer before, 4a4 is the correct answer, and 2a4 is what they got wrong. They were half right. They just forgot to do this bit, which gives you this bit. Okay, so be really, really clear that you have to distribute the power on the outside that you're raising everything to everything there. So let's look at this with one last example before I'm going to let you go and have a practice at those worksheet questions. The answers to those questions will be in the description. But what have we got here? We've got 3a b squared raised to the power 3. Well, again, most students would just do that bit there. They would only times 2 and 3 together, and they would write 3ab6, which is completely wrong, because they've ignored the other two terms, the 3 and the a. The first thing you should realise, right, 3 doesn't have a power, but I know, based upon what we've learned today, the power is technically 1. So I can just slip a 1 in as the power. And that would be exactly the same story for the a. There's technically a 1 as the power. And then you remember I need to distribute this 3 and use the law where I times across the powers to each and every one. So what does that give me? Well, I've got 3 with a power of 1 times 3 is 3, so that gives me 3 cubed, because I've times 1 and 3 together, and that's 3. And then I've got A with a power of 1 times by 3, because the law states we times, so 1 times 3 is 3 again. And then finally, you got B squared times by the 3, so that is B to the power 6. And I'll explain why this is. I'll show you why. Much like I showed you why law 2 worked, I'll show you why this works. But we're not quite done, because we know, don't we? If I colour coordinate this for you, we've got the 3 that goes to 3 cubed. We've got the a to the 1 that goes to a to the 3. And then we've got the b squared that goes to b6. Well, we're not quite done yet, because we know that 3 cubed means 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. So we can actually say that this is in fact 27 a cubed b6, because the 3 cubed can be worked out to be 27. So why does this work? Why do you have to distribute it across? Well, let's take example 2 as our case study. We focus on example 2. What does squared mean? Squared means times it by itself. So that technically means I need to do 2a squared times by itself 2a squared. And if you think back to example 1 on law 2 where we multiply, we can do 2 times 2, which is 4, and then a squared times by a squared, add the powers, a4. So that is why you get, and why you have to distribute it across. Okay? So, quite a few examples that we followed along and explained there. They are the first 4 laws. If you are in higher or in a higher ability set, Indices 2 will take you into some harder laws. But everybody, no matter what set you're in, higher foundation, need to be able to do these laws that I've just explained. These are on the foundation and on the higher paper. So if you're not even at GCSE yet, if you can get good at them now, it's going to make your life a lot easier. Easy marks in the exam. What I've put at the end for you is some questions to do, and I've put a few notes on there for you, but the answers to those will be in the description box below. Hopefully you followed along, hopefully you learned something, and I'll catch you in the next one.